Hello and welcome back to the Chemistry Made Simple podcast. In this episode, we're going to be talking about the acid dissociation constant, Ka, and we're going to talk about how to use it to calculate the pH of weak acids. I'm your host, Matthew Macario. I'm a chemistry tutor, and I'm also a mentor and a coach to chemistry students too. So no more delay, let's get on with the episode. Let's get on with this lesson. Today we're talking about the acid dissociation constant, Ka. That's a capital K with a subscript A. And Ka is applicable to weak acids only, it's not applicable to strong acids. So what is the acid dissociation constant? What is Ka? Well, Ka is the equilibrium constant for the reversible reaction of the dissociation, the ionization of weak acids, and we'll look more at that in a moment. Just like any other equilibrium constant, this is constant at constant temperature. So when you're quoted with a Ka value or you quote a Ka value, it refers to at a particular temperature. If the reaction is done at a different temperature, you will have a different Ka value. And again, just like any other equilibrium, if we're going to calculate the Ka value, our acid dissociation must be in equilibrium, and we'll look in a moment at what that equilibrium looks like. So I mentioned weak acids a couple of times already. What is a weak acid? A weak acid is an acid that only partially ionizes in aqueous solution. That means that only a proportion of the molecules ionize to give the H+ ion and an anion. The alternative type of acid is a strong acid where every molecule will dissociate to give protons and anions. With weak acids it's only a proportion, and it tends to be a small proportion of the molecules that ionize into H+ and anion ions separately within the solution. And most organic acids are weak acids, but that doesn't mean that all weak acids are organic acids. There are inorganic acids that are also weak acids too. Let's consider what we mean by the dissociation or ionization of a weak acid. And to do so, we'll use Ha to represent a weak acid, to represent the formula of a weak acid. The H of the Ha formula, of course, represents the hydrogen or the proton when it dissociates, when it ionizes, and the A represents the anion when that dissociates. So the equation for the dissociation, the reversible equation, is Ha aqueous gives H+ aqueous plus A- aqueous. So that's Ha, the undissociated, unionized acid molecules, give us the ionization products of H+ ion and A- the anion. If you're watching rather than listening, you'll see that the reversible arrow symbol, the bidirectional arrow, is there to show that this is a reversible reaction. So we start with acid molecules. We can't start with individual protons and anions. You just can't do that. Let's consider some examples of weak acids. The first one we're going to talk about is ethanoic acid. Ethanoic acid has the formula CH3COOH. When we write the equation for the reversible reaction of the ionization, we have on the left as our reactant CH3COOH aqueous, and to the right of the arrow we have H+ aqueous and the CH3COO-, the ethanoate anion. Another example is nitrous acid, HNO2. This is an example of a weak acid that isn't an organic acid. And the equation for the ionization of nitrous acid has on the left as our reactant HNO2 aqueous. Then we have our bidirectional reversible arrow. On the right we have our aqueous H+ and our aqueous anion NO2-. And another example is hydrofluoric acid, HF. Again, not an organic acid, but it is a weak acid. It doesn't completely ionize in water. And our equation is our reactant on the left, HF aqueous, and on the right of the bidirectional arrow we have the H+ aqueous and F- aqueous, the proton and the fluoride anion. So let's think about how we show the expression for Ka, for the acid dissociation constant. So let's consider that generic equation for Ha, our generic weak acid, to start with. So we start with our aqueous acid, HA, our generic weak acid, and we have to start with the acid. We can't start with the anions in this case. That's because the products of this ionization are not individual substances that you can isolate on their own. You can only start with HA as the weak acid. It's a reversible reaction. Our products are our aqueous proton and our aqueous anion. So that's our chemical reaction for this reversible reaction of ionization of our acid HA. How do we write an expression for Ka? Ka being the equilibrium constant for this reaction, and more specifically, it's the acid dissociation constant. So if you remember from our last episode when we talked about how to set up the expression for Kc, the equilibrium constant, that was equal to the concentration of products over the concentration of reactants. Both the concentrations of products and the concentrations of reactants are raised to the number of moles of each in the equation. So in this case, the moles are always 1. There's 1 mole of HA, there's 1 mole of H+, there's 1 mole of A-. So we don't need to worry about writing those ones in. We don't need to consider raising any of the concentrations to a power. So let's write this expression. Ka equals the concentration of products over the concentration of reactants. So H and A are our products, and HA is our reactant. Hopefully you'll also recall from our last episode, if you've listened to it or watched it, the square brackets mean we're talking about the concentration of those species, those substances, in moles per decimeter cubed. So how do we go about working out the pH of this acid now that we have the expression for Ka? This is something you'll likely be asked to be able to do. If you're given the Ka value and the initial acid concentration, you'll need to be able to work out the pH of that acid. So let's revisit how do you calculate pH. To do that, you need to have the concentration of the H+ ion, the protons. Because pH is equal to the log to base 10 of the proton concentration, the hydrogen ion concentration. So how do we calculate that? If you know the Ka value and the HA value, the concentration you started with, how can you work out the concentration of H+ when actually you've still got a second unknown, you've got the A- as another unknown? There is a way of eliminating the concentration of A-, as long as you're dealing with a weak acid only and not with, for example, a buffer. To do that, reconsider the chemical equation for the ionization, where HA dissociates to give 1 H+ ion and 1 A- anion. So that means that the concentration of H+ and the concentration of A- are going to be identical, because every acid molecule that dissociates leads to 1 H+ ion and 1 A- ion. Therefore, the concentrations of H+ and A- are going to be identical. So we've already stated here the correct expression for Ka, for the acid dissociation constant. And that's what you should always be quoting if you're asked for it in an exam question or any other question, in fact. But now you've quoted that, you can then modify it. And we can do that by replacing the A- concentration with H+ concentration, because we've deduced that they are identical. So if you do that, if you replace the A- concentration with an H+ concentration, you get that the Ka equals H+ concentration times H+ concentration divided by HA concentration. And of course, we can represent that better like this. Ka is equal to H+ concentration squared divided by HA concentration. Or to put it another way, Ka equals the concentration of protons squared divided by the initial concentration of the weak acid. So in order to calculate pH, when we knew the acid concentration and the Ka value, we can rearrange this equation to calculate the proton concentration, H+ ion concentration. So if we multiply both sides by the acid concentration at HA, we have Ka times HA, the acid concentration, equals H+ concentration squared. And simply square rooting both sides means that our H+ concentration, our proton concentration, is equal to the square root of Ka times the HA concentration. And of course we have those values for Ka and the initial acid concentration HA. So we just put those numbers into the equation, do the calculation, and we come up with our hydrogen ion concentration, our proton concentration. And then you can just put that H plus ion concentration into the pH calculation that we just talked about a moment ago. And that's a simple calculation to come up with the pH. I hope you found this episode will help you with the acid dissociation constant, with how to calculate pH as well. If you have found it useful, please like the episode and let me know what your biggest takeaway is in the comments below. Don't forget to subscribe to the channel too, so that you don't miss what I've got coming up for you. At this point, I want to say a big thank you to you if you're one of my Patreon patrons. Your support of this podcast is really welcome. I want to thank you. And if you're listening and you're not a Patreon supporter yet, then you can do so at patreon.com/chemistrymadesimple. Every bit of support really helps. If you have any questions about what I've talked about in this episode or any other of the chemistry syllabus, or you have suggestions about what you'd like to hear in another episode, then please get in touch with me. You can do so on my Patreon, also on my email, that's matthew@chemistrymadesimple.net, or on my Instagram where I'm at chemistrymadesimple. If you'd prefer, you can also leave me a short voice note, and you can do so at chemistrymadesimple.net/voice note. However you get in touch, I really appreciate hearing from you, and I do get back to everyone. With that, we'll bring the episode to an end. I look forward to seeing you next time, and until then, do look after yourself. So here's those details again. Don't forget to subscribe to this channel. You can also leave me a voice note, contact me on Patreon, DM me a message on Instagram, or use my email address. Use whichever is easiest for you. And I will get back to you when you do get in touch.